Welcome back to the third video of the series. Today we're going to talk about our computer's memory map and how the x86 handles interrupts. But before we start, let me kindly ask you to help in creating this channel. If you find these videos useful or interesting, please consider leaving a like and subscribing. It costs you nothing, but is vital to this channel's existence. Thank you for your support. In the previous video, we attached a flash memory to run our first program. Doing so, we wired its chip-enable signal to the ground, as it was the only memory device attached to the address bus. Today, we'll add the 512 kilobyte RAM chip, so we need to make a decision on which part of the whole address space each memory chip will be visible to the CPU. I'm sure that until now you remember that the x86 starts executing code after reset from the address of FFFF0 hex, which is at the very top of the whole 1 MB address space. That determines that our ROM needs to be visible at the top as well. On the other hand, interrupt vectors are located at the very bottom of the address space, where we are going to place our RAM to. To avoid unnecessary complication, let's divide the whole 1 MB address space into two halves, the bottom one for the RAM and the top one for our ROM. We don't need to worry too much about more devices we will attach in future videos, because they will be accessed by the CPU in the separate I/O address space. Halving the whole 1 MB lets us use only the most significant address bit, the A19, to decode whether our CPU wants to talk to the RAM or ROM. For the bottom half, the A19 is low, and for the top one, high. Because the chip-enable signal is active low, we could simply connect the A19 directly to the RAM's CE pin and invert it for the flash chip to become active when the A19 is high. But let's not forget about the two distinct address spaces of the x86, the memory one and the I/O one. We want to activate one of the both memories only when the CPU addresses the memory space, which is indicated by the high level of the IOM pin, and keep them inactive when it is low. Here is what we need to build. The NAND gates seem to be an obvious choice because they output 0 only when all inputs are high, and this is the active level for the chip-enable signal we want to generate. Unfortunately, our IOM pin is low for the memories, so we need to invert it first. Then we have two NAND gates, each for the RAM and the ROM. One of their inputs is driven by the inverted IOM signal, the other inputs are connected directly to the A19 for the ROM, as this time the high level will activate the gate's output, and invert it using the fourth gain in that chip for the RAM. For those not familiar with NAND gates and others, I'd like to recommend my new upcoming series on 7400 logic chips. Please subscribe if you don't want to miss it. Before we start building our decoder of chip-enable for both of the memories, which will be built using this 74HCT004 NAND gates, I'd like to add the RAM memory, which in my case I'm going to use this 628512 RAM, which is 62 means that it's a RAM memory, 8 means that it's 8-bit memory, and 512 obviously is the capacity, which is half meg, 512 kilobytes. It is a 32-pin DIP package, exactly the same as the flash memory, which is 4 times smaller. And I thought I could obviously put the RAM here. That was my original plan, but I thought that since we're going to change our program in the flash memory quite often, why not to use the ZIF socket, which is quite massive and takes quite a lot of space. So I thought if I moved the flash to this edge of this breadboard, then I will replace it with the RAM in the middle, which means I need to change a few wires because most of the pins are the same in both memories, the flash and the RAM, but there are 3 differences: A14, A15 and write enable are swapped over. And also, of course, in place of non-connected 2 pins in the flash, we now have the 2 additional address lines, A17 and A18. So let me just replace this flash with the RAM. It was here. and then I'll build in this ZIF socket here and connect all the data and address common for both between them. Okay, I think I finished connecting all common pins for both of the memories. Now I need to connect A14 and A15 together. A14 is here at the top in the flash memory, but in the RAM package it is pin number 3. A15 in turns is pin number 3 in the flash and pin 31 here. Pin number 1 is not connected, as well as pin number 30 isn't connected. Pin number 31 is write enable, which we won't use, so we need to short it to VCC. We're not planning to program the flash memory in system. If I take this out for a moment, then add this to VCC and pin 30, then this can go back. This is not connected, this is not connected. The missing one is pin number 2, which is A16. A16, oh, that's pin number 2 in the RAM as well, so that is gonna be easy. Okay, looks quite okay. I think if we just returned the, oh, we've got a read signal from the CPU here, and that is output or chip enable, which is now shorted to the ground. And read enable goes, I connected it back to this flash space here. So I believe we could, we need to just switch output enable here and disable for the moment. If we disable for the moment our RAM by putting its output enable to 1, we can theoretically try to install the ZIF package back here, put our flash memory in, and we can just test quickly if we didn't make any mistakes in connecting those. So it looks like everything is okay. Our program from the previous video still is working. What we now need to do is to connect chip enable of the flash and chip enable of the memory, RAM memory, to our contraption using 74HCT00. We will find out very soon if our computer, together with freshly added RAM memory, works as expected when we start it in just a few minutes. Every processor has a means for a device on the bus to let it know that the device needs its attention. It could be a keyboard controller telling the CPU that a key has been pressed, or a communication device receiving some data. It is usually done by activating an input signal of the CPU, usually called interrupt request. In fact, it is usually 2 pins, but we'll get to that in a second. The processor recognizes the activated pin and interrupts, hence the name, executing its current program and starting a procedure called interrupt handler. It is a special program to talk to the device needing attention in order to receive or send the data the device needs to exchange. When this handler finishes its work, the CPU returns to the previously interrupted program. As I have mentioned, there are usually two pins and we already met them in the first video. They were pin 18, the interrupt request, and pin 17, the NMI or non-maskable interrupt. The difference is that the first one, inter, can be programmatically ignored or masked when the software the CPU is executing should not be interrupted, while the NMI, as its name suggests, is always handled unconditionally. How does the processor know where the interrupt handler is located in memory? In the 6502, for example, it is trivial. The last 6 bytes at the very top of the memory hold 3 16-bit vectors, telling the CPU where to jump to in order to handle the non-maskable interrupt, the reset, and the interrupt request accordingly. But this solution, while being simple, has its drawbacks. Since there is only one common interrupt handler, there is no way to tell which device raised the interrupt. So the interrupt handler usually needs to ask each device, "Has it been you?" in order to handle the request. It is slightly more complex in the 8086. We have not 2, apart from the reset vector, but 256 distinct vectors to be allocated for each device. To make it even more complicated, the interrupts may be raised not only by the signals on those 2 pins of the CPU, but also by the CPU itself or by the software. We will attempt to raise all types of interrupts and see the CPU's response in a minute, but first we need to learn how the CPU knows which of the 256 vectors to use at a time. Some of the interrupts are simply assigned each to a particular vector. Intel reserved the first 32 vectors from index 0 to 1F in hex to be processor generated. 5 of them were used in the 8086 and many more were assigned in later designs, starting with 8286, where memory protection and virtualization were added. Requests on the NMI pin will always invoke a vector at index 2, for example. If a program attempts to execute a division by 0, the CPU will raise an interrupt at index 0. In the next video, we will heavily use yet another CPU-generated interrupt, which will let us see the processor's internal state in much more detail than what these rows of LEDs on our breadboard show us. The interrupts can also be generated by software. There is an instruction called int, which takes an 8-bit operand, telling the CPU explicitly which of the 256 handlers to execute. They are usually used to call functions of the operating system by the user's application. If you had a chance to program for MS-DOS, you would know too well the int21 hex, which was the common entry point for most of the MS-DOS functionality. Finally, let's talk about the interrupts raised by the inter pin. It is slightly more complicated and usually supported by the additional chip called the Programmable Interrupt Controller, or PIC for short. The PIC has 8 separate interrupt inputs, which can be used each by a different device. It can also be programmed to assign a specific vector to each of the 8 lines. The CPU uses the inter in pairs with the int A, interrupt acknowledge, to communicate with the PIC. When a device raises an interrupt via the PIC, which asserts the inter signal, the CPU starts to handle the request. It does so by asserting the interrupt acknowledge signal back to the PIC, which in turn tells the CPU, via the data bus, which vector to use to handle this particular request. It may sound complicated at first, but it will become clear when we try to simulate this in our breadboard computer without using the actual PIC. But before we do that, first let's see what happens when we raise the NMI request. To be able to raise an NMI interrupt, we first need to replace this jumper down here, which shorts the NMI input to the ground, with a resistor, which will just pull it down, and with a wire, let's say yellow, which we then touch to the VCC, which will raise an NMI interrupt. We've got the hardware ready, now let's have a look at the software. Today's program is a little bit longer than the last one. This time we need to set up a few things, and we certainly cannot fit in the last 16 bytes of the address space. Therefore, we start with a jump to another area of our ROM. Let's use the last whole 64 kilobyte segment of memory, starting with an absolute address of F0000 hex. Therefore, the first instruction after reset is a jump to segment F000 and offset of 0. It is called a far jump, where we specify a new value for both the segment and the offset. The offset in this case is given by the init label, which is then replaced by the compiler with the real value where our code is. Because now we need to use our freshly installed RAM, the next thing to do is to set the correct values of the segment registers, including the SS stack segment register. Just as a quick reminder, most processors use the concept of stack. It is an area in RAM whose idea is similar to a physical stack of things, let's say books. You can put another book on top of it or pick up the one from the top. In computers, we say that we either push data on stack or pop them back. The CPU uses the stack to save the return address where it needs to come back after jumping to a subroutine or a function. The 8086 has the call instruction, which does exactly that. It jumps over to the specified address of a function, but first it saves its current IP register's value in pairs with the CS for the far call on the stack. The function then needs to finish with the ret instruction, or retf for the far call again, which pops the saved IP register and optionally the CS, causing the CPU to return back to the instruction following the call to carry on. Of course, the function can call other functions, which can call other functions, and so on, but thanks to the stack, the CPU always goes back to the most recently saved return address, while still keeping the whole history of calls. There is one important thing to remember though. Unlike the stack of books, stacks in most processors, including the 8086, grow downwards, meaning that the next data on the stack is saved at a lower address in memory. This information helps us set up the SS and SP registers correctly. Let's see the memory map of our computer. Because the stack grows downwards, we can initiate it at the top of the RAM, which ends at 7FFFF hex. The last full 64 kilobyte segment of the RAM starts at 70000 hex, so the SS needs to be set to 7000 hex. What about the initial value of the SP register? We could set it to FFFE hex, not FFFF, as the stack in 8086 operates on 16-bit data and the offset should always be even, but we can also use the fact that the CPU decrements the SP before the data is stored to the address pointed by its value. Therefore, we can set it to 0, and the first push to the stack will decrement it by 2, wrapping around back to FFFE hex, and the first 2 bytes will be stored at 7000:FFFE, effectively in the last 2 bytes of our RAM. So let's do that. We now know that we need to set the SS to 7000 hex and the SP to 0. The first 2 instructions set the SS via the AX, as the segment registers cannot be assigned an immediate value directly in one instruction. But you may wonder what the next instruction does. Why is it not move SP0? Well, XOR applies exclusive OR logic operation on each bit of the 2 operands. If you're not sure what exclusive OR is, I'd like to recommend to you my upcoming series about 7400 logic chips. It's not yet available at the moment of publishing this video, but I'm planning to cover all basic logic gates in October. Okay, back to our XOR SP instruction. Shortly speaking, XOR compares bits in both operands, and the outcome is 0 when they match and 1 otherwise. In this case, we use the same register for both operands. That means that the XOR operator will always yield 0 for each bit as a result, whatever the value in the SP originally was. In other words, XORing a register with itself always produces 0, so it is a way to set any register to 0. You might ask, why did I not simply use move SP0? Let's look at how both instructions are encoded in the machine code and executed. As you can see, XOR SP compiles into 2 bytes, where the move SP0 takes 3 bytes. That is because the immediate number, which is a 16-bit value, needs 2 bytes to encode. The first BC simply encodes a move an immediate value to SP opcode, which is then followed by 2 bytes of the value itself. Now let's look at the time required to execute both of the instructions. The move one takes 4 clock cycles and the XOR one takes only 3. So the XOR is not only shorter, thus requiring fewer bus cycles to read from memory, but it is also faster to execute. This is the reason why you would never see the move instruction to set any register to 0 in code produced by any high-level language compiler. Assembler programmers knew that as well and were always using XOR for that. If you think this digression was unnecessary here, or maybe you would rather find a separate mini-series about x86 assembly explaining all instructions useful, would you let me know in the comments, please? I appreciate any advice on how I can make my videos best for all of my audience. Thank you for your input. The next step in our initialization code is to configure the NMI interrupt handler. The handler itself is trivial. It consists only of the NOP instruction, which you already know, and the mentioned before IRET, which will make the CPU return to its normal program. But how do we tell the CPU where to jump in case of the interrupt? As I said before, the x86 can handle 256 different interrupt vectors. They are all stored at the very bottom of the whole address space, starting from the absolute address of 00000. This is why we set both DS and ES segment registers to 0 using the current value of the SP. It is simply an array of 256 pairs of the IP and CS values, both being 16 bits or 2 bytes long. That means that each vector takes 4 bytes in memory, and therefore, if we want to calculate the offset of the nth handler, we need to multiply the n by 4. That's what this instruction does. The 2 is the index of the NMI handler in this array. Why did I use the DI register for that offset? If you look down, you will notice the STOSW. The name is short for store string word. It is one of those instructions which operate on strings or blocks of memory and use certain CPU registers implicitly. I mentioned them in the previous video when I talked about the x86 registers. This instruction doesn't have any operands because it always stores the AX into the memory address pointed by the ES and DI pair. It also increments the DI by 2, allowing us to store the next value of the AX in the following 2 bytes of memory using another STOSW. So this short instruction does quite a lot of work for us behind the scenes. The compiler will replace the second operand offset NMI handler of the move AX during compilation with the actual offset where the interrupt handler exists using its label. The second value of the AX, which is the segment part of the handler's address, is taken directly from our code segment register CS, because we compiled all our code into the same 64 kilobyte segment of ROM. We know for sure at the moment that it is equal to F000, but there is no point in hard coding this value if it's available in the register. Then the code is just an infinite loop of a NOP and the jump back. We are going to break out of this loop using the NMI interrupt in a second. You may ask why I spent so much time talking about the stack before testing how our processor handles interrupts. Well, interrupts, as the name suggests, interrupt executing the regular program when they happen, and the CPU before handling them needs to store the place in the program where it got interrupted to carry on after. Just like calling a subroutine, but it may happen at any moment, not as a result of executing the call instruction. To be precise, there is one more difference. When the CPU is interrupted before storing its current CS and IP values, it also additionally pushes the current value of its flags register to the stack for us. Because of this difference, the interrupt handler procedure needs to finish with a matching return instruction, the iret, which pops all three values back from the stack, the IP, then CS, and then the flags register. I think we have covered all the theory behind our program. Now let's see it in action. Because you already are familiar with how the x86 starts after reset and how it reads and executes its program, I've gone through step by step off of the camera until it enters our infinite loop, where it waits for an interrupt to happen. I must admit it was quite a few clock cycles until I got here. What you can see now is the first clock cycle reading a NOP instruction in our infinite loop, which is under F0015, and that is byte of value, you know that already, right? 90, which is NOP. Then in the next cycle we have the following address, which is F0016, and that is reading the first byte of the jump instruction, which is EB. Let's go through that, and the next one is F0017, which is the second byte of the jump instruction. It's a relative jump requiring only one byte, which is FD, as you can see. It is now prefetching the following bytes after the jump, even if it's not gonna get there. And that's why I included those 4 NOPs after the jump, just to separate our loop from the NMI handler, so we can clearly see when the processor is reading our handler program. So while generating the clock, I am now going to raise NMI high. It could be a momentary one, so I'm turning this back to 0. And now let's see what's going to happen. Now it tries to still prefetch a next instruction, which is currently F0018. Now we've got a few cycles where nothing is happening, and that's probably because the CPU just executes the NMI procedure. We need to wait until the next ALE signal is raised, and that's it. And let's have a look. It is still executing our normal program because now it reads the NOP from the beginning of the loop. But I'm sure shortly we'll see. And there you go. That's something new. As you can see now, the processor addresses the very, very bottom of the memory, address of 00008, which is in our RAM. And as you remember, that's the index where the NMI vector sits in the memory. Let's see what is it going to do with that. It's going to read memory, and the memory contains 1C. 1C is an offset of our NMI handlers, so that's what's expected, because as you remember, the vector consists of first the IP value and then the code segment CS value of the procedure. So that's the first byte of the IP part of the vector. The next byte at offset 9 is just 0, because the offset of our NMI handler is 001C. That's the most significant byte, which is 0. And now in between, that's quite interesting, and remember that this is because what we see on these LEDs is just a state of address and data buses of the processor. We don't know what the CPU is actually doing at the moment. So once it's read the IP part of the vector, it's still carrying on prefetching bytes of our normal program. And now in the next bus cycle, as we can see, it keeps on reading the RAM, which is now offset 0000A, which is the CS part, the segment part of the vector. And as we can expect, it should be F000. So the least significant byte, which is 00, and at the offset of 000B, we should get the F0 part. And as you can see, this is in fact F0. Okay, so the CPU now knows where to jump in order to handle our NMI interrupt. Let's see what is it gonna do next. Again, nothing is happening on the bus, but believe me, the CPU does lots of things under the hood. And as you can see, next bus transfer, that's quite interesting. And that's what I was talking about before. Now it tries to access the address at the top of the RAM, which is because the address is 7FFFE. So that is the second to last byte in the RAM. So we may expect that the CPU will try now to store the 3 values it needs to store on the stack in order to jump to the NMI handler. First, it's the flags register, then it should follow with the CS, current CS, and the third word would be the current IP value. Let's try. So that is the flags register, we believe. Yeah, and it's writing now to the RAM value of 46. That's the least significant byte of the flags register. And then we expect it, yes, to address the last byte in our RAM, which is 7FFFF. And the value of this byte is the value of this byte is F0. It's writing F0 to this byte in memory. So it means that the flags register at the moment contained values F046 hex. We will talk about flags register in the next video a little bit more. For now, just remember that before handling any interrupt, the first thing the processor does is to store its current value of flags register. So now we should get to the next bus cycle. Not much is happening. Any changes which you can see in the LEDs don't really matter until we see ALE active, which is now. And now the CPU will try to access 7FFFC. So that's the 2 bytes before the previous write, because the stack grows downwards, as you remember. The next 2 bytes will be written under this address. And that's what we expect should be the current value of the CS code segment register. And it's writing 0, that's the least significant byte of the F000, so that's 00 currently. And the next transfer, we expect it to be the next byte in the RAM, and the most significant byte of F000 is, as you can see, F0. So that's all fine. So now the next transfer, we expect it to be the current IP instruction pointer register stored on the stack. But that's not necessarily what happens on the bus. Remember that what we can see here doesn't necessarily reflect what is CPU doing, because now CPU is busy trying to switch to the interrupt handler, while it already knows, because it read from the memory, the vector, so it knows where to jump, and even before storing the current IP value to the stack, it already tries to prefetch the NMI handler, because what you can see is the address of F001C, which is the address of the first byte of our NMI handler. So that's quite interesting, but also quite confusing sometimes, because you kind of see the things happening on the bus out of step. And that is 9-0, because that's obviously the NOP instruction. And the next transfer is the our stack, probably, because it's the address of 7FFFA. So that means that the stack grew downwards again, and from FC it jumped now to FA. We expect that the CPU will now store its current instruction pointer. Let's see, it writes the value of 1.5, which is the NOP instruction in our main program. And the next transfer is probably 0, because that's the older byte of this offset 0015. Let's see. Yeah, that's 0 written to the following byte. So now that's the moment where the CPU already stored all information on the stack which it required to do, and read and also read the first byte of our handler program. It says probably executing it now. So let's see what happened. Oh, I just accidentally pressed the clock twice, but ALE switched on for a moment. So it is the next byte of our NMI handler program, F001D. Yeah, that's our IRET instruction in our handler, which is CF, correct? And now the processor is probably executing either the NOP in the handler or already IRET. Let's see, what is it doing now? F001E. That means it tries to read the following byte after our procedure. And that's probably, yeah, it's just a 0 random byte from our flash memory, because there is no other program stored behind IRET. CPU doesn't know that and just tries to prefetch more bytes to execute. What will happen next? That's yet another prefetch, F001F, which is again 0. And then look at that, something changed. I'm guessing that the CPU just finished our NMI handler, and now it tries to pop all the values it pushed to the stack back, because it's trying now to return to our main program. The address on the bus is 7FFFA. So now it tries to read from the stack the last value it pushed on it. So that's, let me remind you, the instruction pointer register value, which was 1.5, and the older value was 0. Yeah, that's the next byte addressed on the stack, and now it reads value of 0. Next thing it should do is to probably read the code segment register pushed on the stack. Now it's busy doing things, and yes, look at that, 7FFFC, which is the place where the CPU pushed its code segment value, which was, yeah, the least significant byte is 0, and the most significant byte or older byte is F0. We'll see it in a second. Yeah, F0. The last thing to do before coming back to the normal program is to read the flags register from the last 2 bytes on the stack. Let's see if it happens. Yes, 7FFFE. The value read from it is 46. And the last was, I guess, F0 from what I remember. Yeah, that's the last byte in our RAM memory. And value read is F0. So now I guess the CPU should just carry on with its normal program. And yes, as you can see, it already tries to prefetch the next byte, which is exactly the byte of our normal program, which address was stored on the stack before handling this NMI interrupt, which was F0015. That's a NOP, and it just goes on and on in our infinite loop, waiting for yet another interrupt. As you can see, looking only at the CPU buses can sometimes be a little bit confusing, as things happen out of step from the program. It is fun to see these details during a few instructions, but for more complex programs it may not give us a proper view. That's why I'm planning to change that in the next video after we see how the PIC talks to the CPU handling inter requests. That's how the 8086 handles interrupts. This experiment showed only the simple case, where the NMI request has a predefined interrupt vector, number or index. As much as I'm really keen to show you how the CPU talks to the PIC or Programmable Interrupt Controller, I think we need to leave it for another video, as this one is already quite long and we covered quite a lot of theory here. Next time, after we simulate the PIC telling our 8088 which interrupt vector to use in response to the inter request, we will attach the first I/O device to our computer and attempt to change the way we look at its interworking. I'm planning to get rid of the LEDs and the manual clock generator completely and using one of the hardware-generated interrupts, which we haven't mentioned yet, instead. Until then, I really hope you enjoyed this video. Thank you all for really warm comments on my work so far and lots of likes. Please consider subscribing if you hadn't done so and leaving a like or a comment. I hope to see you next time.